When divers start exploring deeper than recreational depth, they start encountering problems that cannot be fixed through training alone. The very gases that they breathe become a problem. This is why technical divers often replace some or all of the nitrogen with helium. In this episode, we'll explore the science behind helium diving, how it behaves underwater, and how it affects the body. To understand why helium is used, we first need to explore a little bit of the physics behind diving and behind breathing underwater. Here at sea level, the air contains approximately 21% oxygen and 79% nitrogen, a perfect mix for keeping us alive. But as a diver descends, the ambient pressure starts increasing. We call this Boyle's Law, and we have an entire Scuba Science episode about this. In a nutshell, here at the surface we experience 1 bar of ambient pressure. For every 10 meters or 33 feet that we descend, an additional bar of ambient pressure gets added. This means that at 10 meters we experience 2 atmospheres, at 20 meters 3 atmospheres, 30 meters 4 atmospheres, and so forth. Although the percentages of oxygen and nitrogen in the air remain unchanged at depth, the molecules are squished much closer together when we breathe these gases at depth, and therefore their physiological effects intensify. This is what we call the partial pressure, and it is exactly this increase of partial pressure that causes physiological problems at depth. Scuba Science is entirely self-funded, but if you want to support it or the Dive Saga channel in general, you can do so by picking up some merch, which you should find below this video or on the divesaga.com website. Of course, I also encourage you to like the video, leave a comment with a question, and if you can, join the channel. By joining the channel, you support us structurally, and by supporting us structurally, you can also get access to member-only videos, such as the Dive Saga soundtrack and some deep dive video debriefings. Plus, you also get access to the Scuba Science scripts for further studying. The first major problem when using regular air at depth is nitrogen narcosis. Nitrogen is generally considered physiologically inert at the surface, meaning it has no significant effect on our body. However, under increased pressure, it starts to affect the central nervous system of our body. The exact mechanisms behind this are still being studied to this day, but nitrogen is known to dissolve into the lipid-rich tissues of our brain and central nervous system, altering their neuronal function. Symptoms of this include reduced reaction time, a lack of concentration, poor decision-making, and impaired short-term memory. You could see why this could become a problem on deeper, more complicated technical dives. Numerous studies have clearly demonstrated that there is a clear impairment of judgment and cognitive function at depth with even recreational divers. Importantly, narcosis affects each diver differently, but no diver is immune. And yes, experience and repeated exposure may of course help a diver recognize these symptoms earlier, but it does not eliminate them. As depth increases, nitrogen narcosis becomes more and more significant. For this reason alone, air is not considered a very suitable gas for deeper dives. But nitrogen is not the only problem. The other component in air, oxygen, has some nasty side effects of its own when under pressure. Oxygen becomes toxic when breathed under elevated partial pressure. This is why most training agencies will recommend limiting the oxygen partial pressures to 1.4 ATA for the working part of the dive and 1.6 ATA for the resting part of the dive, such as the decompression stops, for instance. If a diver breathes regular air on a technical dive, they will already reach an oxygen partial pressure of 1.4 at 56 meters depth. Beyond this depth, the risk of central nervous system oxygen toxicity increases significantly. Symptoms of this can include visual disturbances, a ringing sensation in the ears, nausea, twitching of the muscles, and dizziness. But worst of all, a diver could end up convulsing underwater. Convulsing underwater would cause them to spit out their regulator, inhale water, and drown. Such an underwater seizure is obviously almost always fatal. So as dives become deeper, not only the nitrogen percentages, but also the oxygen percentages have to be reduced. This means we need a third gas to take up the space. And that gas is helium. Helium possesses several qualities that make it uniquely suitable for deep diving. First of all, unlike nitrogen, helium is non-narcotic, meaning it does not produce these narcotic side effects that nitrogen does, even when breathed at depth. Replacing some or all of the nitrogen with helium allows the diver to retain a significant amount of their cognitive function. A trimix, therefore, may, for instance, allow a diver to retain a similar cognitive function at 90 meters that they would normally have on air at 30 or 40 meters, depending on the amount of helium and nitrogen in the mix. This, of course, substantially increases the diver's ability to handle task loading, their overall cognitive function, and therefore the overall safety of that dive. The second major advantage of helium is that it is a very light gas. Helium is the second lightest element in the universe and is approximately 7 times less dense than air. This becomes important especially at deeper dives because as we descend, because of Boyle's law as we saw earlier, gases become denser when breathed at depth. So having a gas that is naturally less dense is of course going to greatly reduce the breathing resistance in our airways that would be caused just by breathing. At depth, when a diver needs to exert more effort to simply breathe, this of course is going to increase their carbon dioxide buildup. It's going to increase their breathing workload and stimulate fatigue, all elements which we do not want at depth. Carbon dioxide retention is a significant contributor to diving accidents because elevated CO2 can worsen nitrogen narcosis and also make one more susceptible to oxygen toxicity. Helium significantly reduces the breathing resistance compared to non-helium based mixes. And this is one reason why helium is often used even when narcosis is not the primary concern, but simply to reduce the work of breathing. However, at extreme depths, another issue appears: high pressure nervous syndrome, or HPNS. Unlike narcosis, which is associated with nitrogen intake, HPNS is primarily associated with helium intake at extreme depths. Symptoms of HPNS can include tremors, reduced coordination, neurological dysfunction, and cognitive impairment. That being said though, HPNS really only becomes significant beyond depths where even most recreational technical divers will venture, deeper than 120 meters, 400 feet and beyond. And so it's much more commonly encountered in commercial saturation diving or extreme deep diving exploration. Interestingly, they actually end up adding a little bit of nitrogen back into the mix to induce a mild form of narcosis, to subdue the side effects of HPNS, which I find rather interesting. This is actually one of the reasons why extreme deep divers will use a trimix rather than a Heliox mix, again adding a little bit of nitrogen instead of pure helium and oxygen. There are several variations of helium-based gas mixes used in technical diving. The most common one is probably trimix, a mixture of helium, oxygen and nitrogen. Another commonly used mix is Heliox, a mixture of simply helium and oxygen. Common examples of trimix gas mixtures would include Trimix 1845, Trimix 1555 or Trimix 1070. The first number always indicating the oxygen percentage, the second number the helium percentage. The lower the oxygen percentage, the deeper the gas is designed to be used. The higher the helium percentage, the less narcosis it will cause. In the case of Heliox, it will simply contain helium and oxygen and no residual nitrogen. But as mentioned earlier, at extremely deep depths, this becomes impractical. Despite its advantages, helium also introduces several new disadvantages into the mix. The first one is certainly the cost. Of all the diving gases, helium is extremely expensive and not always logistically easy to obtain. It's a finite resource primarily extracted from natural gas reserves. And therefore, a large trimix fill can cost many times more than a standard air fill. And this is also the answer to the question that people often ask, which is why not just use Heliox instead of trimix? The answer being it's simply more expensive. More helium, more cost. A second issue with helium-based breathing gases is heat loss. Helium conducts heat more efficiently than nitrogen. But that also means that divers breathing helium-rich mixes at depth often experience a much faster heat loss through respiration. And this in turn, of course, contributes to greater heat loss during long decompression dives in cold water, which in itself can then again stimulate decompression sickness. So heat loss is definitely a factor and something that needs to be organized against with proper exposure protection. And a last disadvantage of helium is of course also that it changes your voice. This is not super significant on recreational technical dives, but on dives where communication is required, for instance, this can become a little bit of an issue. The key takeaway here is that extreme deep diving is not only limited by equipment and training, it is limited by the gases themselves and the way that our body reacts to them when breathed at depth. Nitrogen causes narcosis, oxygen causes oxygen toxicity, and gas density increases the breathing effort. So deeper diving requires a constant reorganizing of gas percentages to combat these side effects. Helium already addresses two of these major challenges: reducing the narcosis that nitrogen can cause and reducing the work of breathing by gas density. And it is for these reasons that helium has become a foundational gas in deeper technical diving. Whether divers are exploring deep reefs, deep wrecks or caves, or even on commercial ventures, helium allows them to function more efficiently and operate more safely than standard air would. In short, helium is not used simply because divers want to go deeper. It's used because in the realm of breathable gases, there are very few other alternatives that will work for our body physiologically. It's simply one of the ways that we've solved depth limitations by applying scuba science. Guys, remember to subscribe to the Dive Saga channel and click the join button if you can. It supports us in a major way. Thank you so much for watching and I'll see you next time.
If you're into scuba diving, make sure to also follow the Dive Saga Dive Debrief podcast. You can find it on Spotify and YouTube. In this podcast, we cover the behind the scenes of our Dive Saga episodes.